Good morning. My name is Peter Voss. I'm a research scientist in the Natural Resource Ecology Laboratory, and today we're going to be talking about multiple regression analyses. First, there's really four ways in which we can analyze data. And data can either be continuous or categorical. I know that you've already addressed a lot of these different things, but I just want to make sure we review it briefly to make sure we're all on the same page. So a little bit of an overview of linear regressions. It's really to understand the relationship between two different variables, two different continuous variables. To be able to look at that, we need a predictor and an independent variable that is the potential cause of that other variable for changing, the response versus the dependent variable. The predictor variable or the independent variable is usually denoted as an X. The response variable or the dependent variable is denoted as Y. A significant relationship between X and Y does not prove a cause and effect relationship, and this is very, very important. You hear this very often: correlation is not causation, and it's very critical to understand those differences in the way you interpret this kind of information. So therefore, the first step is to really think about what are the assumptions within a linear regression. The first assumption is that there is a linear relationship between X and Y. That's pretty straightforward, and as the figure on the right top is showing, points are distributed throughout with some variance, which we'll talk about how to address later. There's a certain relationship between those two that's explaining how Y is changing as a response to X. Now, one of the most important assumptions within statistics is normality. What is the distribution of your data? If the data does not follow the Gaussian normal distribution, as you see in the right bottom, that's a major violation of these tests. And then if that is not true, that's why we often do transformations to be able to accomplish those kind of distributions so that we can conduct these kind of statistics. If that is violated, none of these outcomes can be interpreted correctly. What's also really important, and which is often overlooked, is the importance of homoscedasticity and its opposite of that, heteroscedasticity. As you can see in the figure on the right top, data that is very much distributed in a heteroscedastic way looks a little bit like a funnel going out. What that means is that the variance is increasing, and the variance is dependent on what the X variable is. That's a problem. That's again a violation of one of the main assumptions that we have, that the variance is not correlating with the actual data. And so the really simple way to think of a linear regression is with the equation y beta 0 plus beta 1 times x, where that way x is predicting y, and we're trying to figure out what values are appropriate for beta 0 and beta 1, where beta 0 is the intercept and beta 1 is the slope of the line. And what we really want, what's really critical, and we'll get into that, how we actually do that in the next few slides, is understanding how to use that error term. And you can see that little term right here, EI, that's really what's referring to what the error is. And using that is how we understand how we can actually draw these lines appropriately to understand the significance of our relationships. So the first step is to find a way to fit a linear relationship. This starts with running a line through the middle of a cloud of data, really simple, and then rotating that line to really reduce the variance. And the way that we do that is we look at the residual sum squares, which is basically where we're having the DI is indicated by the difference between the mean and the actual and the line, which is the mean in this case, and the measurements. By looking at the DI and how that changes, we want to minimize the amount of residual sum squares. If we can minimize that by kind of keep on moving that line, then we can find the optimal value for both beta 0 and beta 1. Now we have found our best fit, we need to find out what our significance values are. The first thing we should do is take a step back and think about what our actual hypotheses are. So our H0 is that beta 1 is 0. There's no relationship whatsoever. The line is flat, fully horizontal. Our alternative hypothesis is that there is a relation between the two and the line is not flat. Now, there could also be an alternative where it's a one-tailed test, but for now we're focusing on the simple H0 versus HA. So you've done a lot of the different approaches in R, so I'm not going to spend a lot of time with it, but I'm leaving those slides here. You can see how to be able to load the data and to do these actual analyses. We're going to focus on interpretation of these results. So we're going to launch our linear regression, and it's going to look something like this in this specific example, where we can see what our minimum is in residuals, what our first quartile is, our median, our third quartile, and our maximum values of the residuals. We see what our coefficient values are, our standard error. And again, what is very important, what our standard error is a standard deviation normalized by the amount of counts, by the amount of samples measured in the data set. By dividing the standard deviation by the square root of the number of observations. So we have that. We have our t-value and p-values, which are really closely associated and are indicatory of how significant our value is, what the level of significance of our relationship. And you can see in both these cases, our p-values are very, very low. 6 times e to the minus 13 and minus 6. That is, as the 3 stars indicate, that is below 0.001 of a p-value. Very, very significant. In the bottom, it's addressing the R-square. It's really important to understand what an R-square is as well. Both the p-value and R-square are really the things that people talk about the most within regressions. The p-value indicating the level of significance, the likelihood of this being true. So in our case, it's below 0.1%. And the R-square indicating how well the data actually fits. How much of the variance are we explaining with the model that we are testing? So in this case, we are explaining about 73% of our variance. A little bit of step back to what an ANOVA is. So we're having our total sample variability, which is explained by the variability in our model, and by the addition of the variability explained by the model, and by the unexplained variability, which is our error, which is the unknown, the part of the components of variables that are controlling our sample variability, but that we don't understand. So then in review, we can get fitted values, we can get residual values for a linear regression so that we can address how likely is this relationship to actually occur and how much of the variance can we explain. And so then now I want to take the step to the next step where we're looking at multiple different variables at the same time, multivariate regressions. What we just looked at was the example of if we're having one X and one Y, and we're just trying to see how one can explain the other. But that's not really what we often do within research projects. We generally have an observed value that we are very interested in. This can be anywhere from looking at wildlife ecology, the amount of deers within the forest, to stuff that I am more interested in is looking at nutrients and carbon cycle in soils. But then there's a lot of things that we measure that we think might be an explanatory variable. And so most of the times, what you're doing in these research projects is you're having dozens and dozens of potential explanatory variables, and you're trying to figure out what is actually controlling the response variable. And so that's what we're going to talk about now. How can we do that efficiently and figure out all the different interactions that might be occurring between those variables? And so then we draw the equation a little bit different than we did for the single variables for the univariate approach. Instead, we still have a beta 0, which is our intercept. That doesn't change. We have a single beta 0, but now we have a beta 1, a beta 2, and a beta 3, etc., etc. However many variables we are testing as an explanatory variable. And they all are associated with a specific variable. So beta 1 is associated with variable 1, etc., etc. We still have our random error assessments, our variance, our population variance, as you can see by mu squared, and all that's the same. Again, the thing that we want to accomplish here is find the equation that fits best. And so at this point, we are in multidimensional space. We're looking at multiple things at the same time. We're still having residuals, and it's important to realize what residuals are. I'm sure this will be on your final test. And so think of that in your simple ANOVAs with discrete data. You're thinking of that as the difference between your error and your mean. In a regression, it's a little bit harder, but it's basically as you're looking at the line and you're seeing the different observations around it, it's the direct difference over the y-axis that indicates the difference between your predicted model and your actual observations. And those residuals are really going to be important in some of the stuff we'll talk about in a little bit. In multiple regressions, we use the least square methods most of the time to be able to calculate what these different, how we can get the best fit and what our residual values are. And we follow all the equations as described for the RSS below. We're going to look at this one example from McDonald 2007, where we're looking at volume, area, weight, and cover. And we're trying to understand how these different variables relate. And so the first step is, and this is really an easy way to kind of visualize what's going on, is to run a full panel scatter plot. The way to launch that you can see in on line 1. And what you're seeing already is that some variables are more likely to relate to each other than others. So you can see the third one on the left, the third one from the top on the left, where we're seeing weight versus volume, are showing that there is likely some kind of relationship. You can immediately visualize where some of this might occur. And that is not the proper way to assess the relationship, but it helps to visualize where things might be going on and to check your work. This is the code you would be calling to be able to launch a multivariate regression. And so let's look at what comes out of that. The output then at this point is showing us volume and area are both highly significant in explaining the data set. There you can see both their estimates, their standard error, their t-values, and the p-values again. Again, the 3 stars are designed below 0.001. You're seeing the discussion on the bottom about the residual standard error. So the residuals are discussed. And here you can see a lot of the other data, the fitted values and the residuals all outlined for this specific examination. Again, this would be the way that we assess it through the ANOVA approach, where we can see our F values and our P values. And again, our F values are the amount of unexplained variance divided by the amount of explained variance. Another way to think about that is to think about it as the variance between different groups that we're testing and within groups. That only really works when you think of it in discrete, but it's an easier way to somewhat visualize what that specific test is doing. But it's very, very closely linked to what the p-value is within all these calculations. So when we're fitting a multivariate linear regression, we will include a variety of different independent variables that are not important. And this is a challenge because the majority of things we measure are potentially not predicting our variable y. If we already knew everything that was going to work, then there was no reason to be able to actually do this specific research problem. And so it's really important to use the right tools to whittle down which ones of your x variables are most important to predict variable y. How do we eliminate those? How do we determine R-square? And how do we prevent bias? It's very challenging here because you can think if you just keep stacking the deck and adding things in there, that you could artificially increase your fit. Model selection, we can do that in several different ways. So we can think of the different sets that you would have with 4 different X variables. But as you can see, and in this situation, the R squared, the predicted value of these different combinations, are displayed on the right. And so as you can see, as you add more variables, you generally increase your explanatory power. So the objective is very simple in a multiple regression model. It is to be able to explain the largest amount of your variance using the least amount of variables. And very importantly, using the least amount of variables is important to prevent having variables that are co-correlating with each other and therefore artificially bumping up your explanatory power. And this is the main thing here is, as I kind of alluded to in the previous slide, is the balancing act between prediction and bias. We want to find the best prediction with the least amount of bias. And so this figure displays that really, really well, where we can see as we increase model complexity, we increase our variance and we decrease our bias error. However, what we want is the total error to be lowest, and that would be in the middle, where we're having intermediate model complexity, and therefore not a lot of error due to variance, and we don't have a lot of bias because we have a proper amount of complexity and not too low. We're not just hedging all our bets on one horse. At the most general level, there are 2 approaches. We're looking at all possible subsets. So if we're having 2 different variables, we can test against x1, we can test against x2, and we can test against x1 and x2. Seems pretty easy. That's not that overwhelming. Now let's do that when we have 20 variables, and I'll let you figure out how many different combinations are. A lot more challenging. And so often what we then use are different algorithms to be able to predict which of these values are the best combination to be able to predict our y variable. Again, these are all the equations, all the different combinations that you could have. And again, this is really, think about this, if we're going to x to the p, let's say xp is 20, how big this would get and how complicated this gets to be able to do it manually one by one. And so we can do all possible subsets. There's also, of course, the approach where you have some a priori, some before you even started studying knowledge or different kind of studies that have already been done. Therefore, you know which ones are most likely to work. And so you might only focus on those different combinations and use those to be able to educate what you're going to test for. An alternate approach, if you're not, that's a little bit more agnostic to it, where you're not really knowing exactly what model might work best, but you have a lot of variables you want to be able to whittle down, is to use a really powerful tool, and I use this very frequently myself, which is AIC, Ikaike's Information Criterion. Basically, what he came up with was an equation that combines the amount of residual sum of squares from the model with the number of observations and the number of parameters in the model to be able to go through several iterations and predict what combination works best without having to do every single one multiple combination. And in this situation, then the AIC, the lowest AIC is the best value. And so you're going to start doing all these different iterations, and you're going to sort them by the lowest AIC, picking the lowest AIC combination, however many variables are in there. And so we have one example where the question is, what affects mussel species richness across different coastal rivers? Coastal rivers are considered isolated habitats that are biogeographic islands. And species richness, which is the number of species that are in a system, were collected in 44 rivers. We included a variety of different independent variables, including the area and the proximity to the river, and as well as different intervening potential rivers, and a variety of environmental quality. We don't need to focus on what these variables are exactly. This is just a case study to show how you might be able to use something like this. So we're going to test correlation among all the covariates. And that's the code how we would do it. And so what we're seeing down here is all the different co-correlations that could occur. And what this is suggesting is that some of these elements, for example, stepping AP versus and stepping AC, are very, very co-correlated. And it's the same for SL and AC. This is a problem. Things that are very strongly correlated are not very much correlated, means that they would basically create a compound effect of your predicted value without actually potentially adding any new information. And so this is a really good example of to start. And it's because there's not that many variables, we can still go through this one by one to see where a problem might occur. And so if we're running that through the model, what we're seeing in terms, I'm taking a little bit of a leap of faith here, but so what we end up with, we're doing all those calculations for a variety of different of these model combinations. You can see that the AIC allows you to sort it out, and you see that it's not necessarily the most complex that wins. So in this case, one of the most complex one is the one that was the most successful. But that it's allowing you to take both the number of observations, it's the bias versus the number of observations you have in the model. It's really taking that ability to get the best prediction with the lowest amount of total error, which is always the most important part of all of this. And you can see that in general, your R-square, which is the explaining the amount of your variance within the model, generally follows the AIC. But that's not always the case. In this example, it is, but it doesn't always have to be the case. Let's see. So at this point, we came to the end of our of this lecture. Thank you very much for your attention. If there are any questions, I'm sure Dr. Schwartz will be able to answer them in a later time. And I wish you best of luck with the rest of your ongoing classes during the semester.